Justin Miller, Oxford College of Physics here. We are going to be looking at some more Kirchhoff, but not for a complex circuit, for something else. So we want to introduce what is known as an RC circuit. We're going to say DC, direct current circuit, like a battery or just a source of potential difference that's constant. And what do we have? Well, what does an RC circuit look like, you may ask? We could take something like this. We've got this. This is a switch that we can close. Here is our source of potential difference. Here is our resistor. Here is our capacitor. So there's an RC circuit. Resistor and capacitor, this is an RC series circuit. They're in series with one another, single loop here, source potential switch. So what we want to be doing with this is looking at the time evolutionary behavior of the charge accumulation on the plates of the capacitor. When we close the switch, it's not instantaneously fully charged, right? That wouldn't make sense because we need electrons to come off of one plate and move around, substantiating a current, but move around and deposit on this plate, right? And when all of the electrons that are going to do it go ahead and cycle over such that the potential difference across the plates of this is equal to that of the source potential, then it's fully charged. But it takes time for that to happen. So that's what we're interested in. How much time and what sort of expression mathematically can we develop, extract out of this system? So we want to find, we seek to determine the charge accumulation on the plates of the capacitor as a function of time. As well as the potential difference across the resistor and capacitor and the current through the resistor with respect to time. So this is what we seek to determine, the time evolutionary behavior of really the entire system in terms of the current, the potential differences across the resistor and the capacitor, and the charge accumulation on the plates of the capacitor. So let's think about a couple things. First, we're working under a condition that the capacitor is initially uncharged. At t equals 0. Second, we close the switch. At t equals 0, then what happens? Well, there's going to be a potential difference across the resistor and, well, eventually across the capacitor as well. So the idea is, once the switch is closed, press the switch. It's closed. Come on over here. The current in the circuit will be substantiated by the electrons moving off of one plate and onto the other. As they move on to the other, plate, there will be potential difference across the plates of the capacitor. Which will increase continue to increase, until the capacitor is fully charged. Delta V sub C is equal to that of the source potential. Once fully charged, current ceases, and the system remains static. As in, nothing else is varying. But this is what we've got going on. So we want to be able to solve this all out and think about some things. So let's get some ideas here. So first, at t is equal to 0, delta V sub C has to be equal to 0. There's no potential difference across its plates because there is no charge accumulated on its plates. When fully charged, we have that delta V sub C is going to be equal to Q max divided by the capacitance of the capacitor from the definition of capacitance, right? So we got these kind of two endpoints there and kind of go with this. So the question becomes, how are we going to get this time evolutionary behavior? And I already hinted at it. You say, well, you already said Kirchhoff. And I say, yeah, I said Kirchhoff. Kirchhoff! All right, so put that up there. And I'm going to erase this part so we can work on this circuit here. And go ahead and employ some Kirchhoff. We look to Kirchhoff. Well, there's no junction in this, right? No junction, so no junction rule. That just leaves us with one thing, a loop rule. This is a single loop circuit. So let us just go ahead and sort of make some notions here. We close the switch. Closed at t is equal to 0. And what's going to happen? Well, we've got, that's the plus side and that's the minus side of the source potential. And, well, that's connected to this, which makes that the plus side and that the minus side of the resistor. We have electrons that are going to come off of this plate and deposit over here. So this has to be the plus side and the minus side of the capacitor as it's becoming charged. So this is what we've got going on. Well, loop rule, whoosh. There's a loop. I'm going to go around it in a clockwise manner. So let's just go ahead and write out what the loop rule is. So I'm going to go across this source potential from minus to plus. So we're going to call it plus. So we got the source potential. We come around. The switch is nothing. We come across the resistor. We're going from plus to minus, so that will be minus. And I'm going to call it minus delta V sub R. So we know that that's the potential difference across the resistor. Then we come across the capacitor, same. We're going from plus to minus. We've got a minus delta V sub C. That's the only three, or those are the only three elements in the circuit. So there's the loop rule. There it is. Ta-da! So what can we do with that, you may ask? Well, this is, again, is just a fundamental law here of conservation of energy. And what we need to be able to do is sort of unravel things a little bit. So let's start to do that, right? So we can rewrite this as E minus I of t times R. That's the same as the source potential, right? Excuse me, the potential difference across the resistor. Current times resistance through Ohm's law. I'm writing I of t because the current is going to be varying with respect to time. If it has to die off to zero as time goes on, it has to be varying. So I'm writing I of t explicitly. This current is a function of time. And then what else do we have? Well, we've got this for delta V sub c. And at any given moment in time, we have that delta V sub c should be able to be correlated with the charge that's accumulated, charge that's separated, and the capacitance. So we've got, again, that's when fully charged. So really that delta V sub c up there should just be the same as this. But we're going to write it like this. We've got Q of t divided by C has to be equal to 0. So at any given moment in time, we have this from the definition of capacitance, we have this from the definition of a resistance, and we note that, yeah, these two things right here have to be time varying in the same way that the current and the charge attenuation vary. So just to make sure we're on the same page with this, we have to have that R is defined by delta V sub R of t divided by I of t. There we go. And that C has to be defined as Q of t divided by delta V sub C of t. By definition, defining those constant resistance and capacitance. All right, so what can we do with this? Well, at least we've got some notion of time in there now, right? So this is what we want to figure out. We want to figure this out. If we can figure this out, everything else will fall out of this. So how are we going to figure out what Q of t is based upon this? Well, what's the definition of current? Current is the time rate of change of charge passing through some point with respect to time, right? So we have that I of t, by definition, is going to be equal to Q of t. That's the Q of t, let me see. D by dt of Q of t. First time derivative of charge passing through some point is the current. And they have to be correlated, right? Because it's the current that's substantiated by the charges moving and really accumulating between the plates. Moving off of one plate, going to the other. So we can rewrite this expression then as E minus, I'm going to put the R first, R times d by dt of Q of t minus Q of t divided by C is equal to, that's right, it's equal to 0. So what do we end up with here? Let's take this a little step further. And if you're not doing anything calculus-based, don't really worry about this. But we gotta get the result from somewhere, so it's coming out of doing a little bit of calculus. That being said, not the calculus base, of course, okay. Let's take this for some sound mathematics that extract out our expression here. So I'm gonna go ahead and I'm gonna take this and I'm going to solve this for d by dt of q of t. So I'm gonna move this to this side, I'm gonna move this to this side, and I'm gonna divide it by r, and we're gonna get ourselves that d, actually I'm gonna move this to the other side, so we've got positives. D by dt of q of t is gonna be equal to e over r minus q of t over rc. Hopefully you see I did that. Took this, moved it over to this side, divided everything by r, and I'm just left with the d by dt of q of t. So this is what we've got to find. We got to find some function q of t that if we take one time derivative of it, we get back some constant minus q of t itself divided by rc. So what is this called? It's called a differential equation. Got ourselves a nice first order differential equation here that relates the rate of change of something to that something itself. So there's some function that solves this. And while we're not going to get all into that, we can do some direct integration with this, or we can use some differential equation stuff to figure it out. But that's sort of secondary. We want to know what solves this. So the solution to this is, drum roll, we've got ourselves q of t is equal to q max multiplied by 1 minus e to the negative t divided by rc. And you probably look at that and go, yeah, I could have guessed that. Just kidding. Anyways, that's a solution to that. I stick this in for q of t right there, and I will get this back out of it, where q of t is this. So I take a derivative of this, and I will get this back out. And we'll show that here in a bit. Actually, let's just show it now. Why not, right? All right. Checking. Switch colors here. So we're going to check this out. Let's look at what dq by dt is. d by dt of q of t is going to be equal to d by dt of q max multiplied by 1 minus e to the negative t over rc. All right, well, q max, that's just a constant. That's the maximum charge accumulated on the plates of the capacitor. And r and c are constants, and then we got the exponential there. Great, we can go ahead and distribute this q max through. The first term is going to give us 0 because the derivative of a constant is equal to 0. So this really comes down to what's the derivative of negative e to the negative t over rc. So this goes to d by dt, negative e to the negative t, excuse me, negative q max. That has to distribute through to that term. Negative q max e to the negative t over rc. So again, the first term ends up being 0, so we're just left with this back end term. And we say, well, what's the derivative of this? Q max is a constant. What's the derivative of e to the negative t over rc with respect to time? Well, that's going to be equal to negative 1 over rc, e to the negative t over rc. So what does this end up being? Well, this is negative q max multiplied by negative 1 over rc times e to the negative t over rc. And as you can see, the negative signs cancel out, and we get that this is ultimately equal to q max divided by rc times e to the negative t over rc. So, what we're saying is that this right here is the same thing as this, if this is a solution. So you say, is this equal to E over R minus Q of T over RC? And there's the question. If it is, then it's a solution. If it's not, then, well, you know what? It's not a solution. Red pin's dying out there. So let's check this. Let us see. What does this turn out to be? Well, you may say those look nothing alike. That's only one term. This has two terms. Where's the e to the negative t over RC? Well, this is still Q of t right here. And we're saying that this here is Q of t. So I'm going to stick that into here now. And now checking out this part, we've got that this is equal to E over R minus Q max times 1 minus E to the negative t over RC divided by RC. So we can go ahead and see what's in here once again. And this is going to be equal to E over R, E over R minus, and then we've got Q max over RC, good. And then we've got a plus Q max E to the negative t over RC divided by RC. So this is what we get out of it. And now you say, well, that doesn't look anything like it. The only thing that matches is this last term with this. Let's then focus on this. If these two things are supposed to be equal, then this better be equal to 0 right here. So what is this equal to? Well, I'm going to take this part now. Focus it on this. Does it equal 0? Question mark. If it does, then we're left again with the two same terms. So we can rewrite this. I'm going to multiply this by C over C and rewrite this as EC over RC minus Q max over RC. Common denominator, then it's a matter of, well, what's E times C? Well, let's go to the definition of capacitance. When fully charged, capacitance is going to be equal to source potential divided by, Q max divided by the source potential when it's fully charged. So what does that mean? Well, it means that E times C is equal to Q max, which means that this is Q max, which means that this is equal to 0, which means that this is indeed a solution because we take the time derivative of it and we get back out this right there. Thank you, Kirchhoff. Thank you, Kirchhoff, very much. All right, so at least we've got a solution, and now we can kind of go from there. So this is what we want to focus our attention on now. Start to see what is in there. All right, so let us just keep going then. So let's see, let's erase some of this stuff and get on with it. So we also need to check is our boundary conditions here, saying that, hey, we said that at t equals 0, that the charge on the capacitor should be equal to 0, and after enough time's gone by, the capacitor should be fully charged. So I've already embedded that in the solution, but it's worth checking. We should have, or we must have, t is equal to 0, Q of t equals 0 is equal to 0. So let's check that. Q t is equal to 0 is equal to Q max times 1 minus e to the negative 0 over RC. What's e to the 0? It's 1. So that checks. We also must have that it's fully charged. Also, it must be fully charged. After some amount of time. We don't know how long that is, so let's just say, hey, what's a really long amount of time? Infinity is pretty long, right? So let's say that Q of t is equal to infinity at Q is equal to Q max. So let's check that out. We have that Q of t is equal to infinity is then equal to Q max times 1 minus e to the negative infinity divided by RC, which is just the same thing as negative infinity, doesn't matter. What's e to the negative infinity? E to the negative infinity is equal to 1 over e to the infinity, which ultimately goes to 0, right? 1 divided by a huge number, that's basically infinity, is 0. What is 1 minus 0? 1 minus 0 is equal to 1, so we're just left with Q max. Q t is equal to 0, excuse me, t is equal to infinity, is indeed Q max. So our boundary conditions check out, and that we get what we should expect to get when we start time and when time ends, or some later time. Now infinity is sort of a relative term here. T equals infinity. Infinity could be a really, really long time, or it could be a really short time. That ends up really depending on aspects of the circuit, what infinity needs to be, well, legitimate. We'll get to that. Let us focus still, though, on this expression for the charge accumulation, and see what else we can get out of this. So we're going to define what's known as a time constant. And you may or may not have seen time constants before. If you haven't, that's okay. And if you have, then you'll kind of know what's going on beforehand, but we still go through it one way or the other. Let us define the RC time constant. Let us define the time constant of the circuit. As RC time constant tau. Tau is equal to R times C. That's it. So why do we choose that? Well, if we look at the exponential term in here is e to the negative t over RC. The units of this term up here have to actually be unitless. We can't raise e to the power of something that has units. It doesn't work, doesn't happen. This has to be a unitless quantity. Thus, R times C has to have units of time, which we're going to use seconds. And if you went through all the stoichiometry for it and broke everything down, you would find that R times C does have units of seconds. So then does tau. So that's kind of one reason. That doesn't really explain why we're defining this time constant. The explanation comes in with looking at t in increments of the time constant. So this is what we have. Let t be equal to 1 tau, 1 time constant, where tau depends on what the resistance is and what the capacitance is in the actual circuit. But we can still define t, or let t be equal to 1 tau. Then we have q of t is equal to tau is equal to q max times 1 minus e to the negative, well, tau divided by tau. because T goes to tau now, right? What is this? Well, this is Q max times 1 minus e to the, what's tau divided by tau? 1. 1 minus e to the negative 1. Hey, that's just a number right there. That's just a number. What does this number equal? Well, three significant figures is 0.632. So we've got that this is equal to Q max multiplied by 0.632. What does this tell us? It tells us after one time constant of time has gone by that the amount of charge on the plates of the capacitor is 0.632 times the maximum amount of charge. Or, after one time constant, 63.2% of the maximum charge is accumulated on the plates of the capacitor. That's a grand. This says that after one time constant, charge plates of the capacitor .632 Q max, or 63.2% of Q max. That's important. One time constant goes by, no matter what R and C are, we have 63.2% of the maximum charge accumulated on the plates of the capacitor. And what can we do with this? Well, we can keep on going. We can say, well, what about after two time constants? What about 3? What about 4? And so on and so on. So let us do this a few times. Say, well, let's look at two time constants, which would be 2 times one time constant. T is equal to 2 tau. We have the Q of T is equal to 2 tau is equal to Q max times 1 minus e to the, oh, that's going to be negative 2. Negative 2 tau divided by tau is just negative 2. That is just a number, and it's 0.865. Just make sure. 1 minus e to the negative 2. 0.865, yes, is equal to Q max times 0.865. So after two time constants, we have 86.5% of Q max. 86.5% of the maximum charge accumulated on the plates of the capacitor. So let's just do a couple more of these. T is equal to 3 tau. Well, we stick it in, we got 1 minus e to the negative 3, and we will have Q of T is equal to 3 tau, 95.0. 95.0% of Q max. T is equal to 4 tau. Let's just stick in a 4 there, shall we? 98.2, we'll call it. 98.2% of Q max. T is equal to 5 tau. Oh my gosh, when are we going to stop? Pretty soon. .3%. And let's just skip to 10 tau. T is equal to 10 tau. 99.995% of Q max, which is approximately Q max. So we say after 10 time constants, general rule of thumb, that the capacitor is fully charged. You may say, well, really, it's going to take an infinite amount of time. I say, well, that comes from treating charge as somewhat continuous here, taking derivatives and stuff. Truthfully, charge is discrete, right? It comes in little discrete packets, 1.602 times 10 negative 19 coulombs. We can't cut it down more than that with the electrons. And there has to be some last electron that goes on there and completes things. Well, if it were continuous, then yeah, technically it'd take an infinite amount of time, but really it's a matter of significant figures. As you go to 11, 12, 13, this gets to 99.999999993, stuff like that. So that is what that is. General rule, we just take 10 time constants, it's fully charged, and utilize this for the time evolutionary behavior of the charge accumulation on the plates of the capacitor. I love saying that. So notice a couple things about this. One time constant goes by from 0 to 1 tau, and we've already got more than half. We've got ourselves 63.2% of the maximum charge. Then another whole time constant goes by, and we go from 63.2 to 86.5%. So first we go well over half the amount, and then the next time constant that goes by, not quite as much, right? We've only got ourselves, what, 23.3% increase from here to there. And then what? Well, we go from 2 to 3. 2 to 3, hey, that's only like 9.5% of Qmax increase. And then we've only got like a 3.2. And then we've only got a 1.1. And then we've only got like a 0.6, 0.7. So what's happening with this as time goes on? The charge accumulation slows down. The charge accumulation is very rapid at first. And then as more and more time goes on, it's slowing down, slowing down, slowing down. That correlates with the current. We close the switch, the current is very quick, very fast current, or very large current, I should say, initially. But as time goes on, well, the current slows down. Why? It's harder to pack more electrons on this as, well, the potential difference across the plates build up. Why? Because, well, electrons don't want to keep coming off of this plate, and they definitely don't want to keep accumulating on this plate because there's already electrons there that are pushing the other ones or exerting a force in the other direction. It just so happens that the source potential keeps pushing them on, but there's more of a, I don't want to say resistance, but resistive type of behavior that ultimately, well, constrains the current, not constrains it, but controls the current, slowing it down over time. Until, well, finally it's fully charged, boom, potential difference across its plates is equal to that of the source potential. Potential difference across the resistor drops down to 0, no more current, and that's that. So that's kind of what we've got going on with this. Pretty nifty. There's some more stuff to look at here, but the time constant aspect regarding the charge accumulation, extremely important. And yeah, that's what we want to kind of deal with at this point. But we're going to look at the other stuff too. So I'm going to erase this stuff and come back, and we'll continue on. All right, so we keep on going. Looking at the RC circuit, what we want to do is, again, sort of see functionally what the representation of the charge accumulation looks like with respect to time. So we can go ahead and draw out something here. Too good there. It's okay. We'll take this to be the time axis. And I'm going to increment this in terms of tau. So taus, 1 tau, 2 tau, 3 tau, they're evenly spaced. So that's great. Let's take this. Tau, 1 tau, 2 tau, 3 tau, 4 tau. So we can take one more. 5 tau. There we go. Time. And then we've got Q of T, the charge accumulation on the plates of the capacitor. What are we going to have? We're going to have some Qmax here. And that's the maximum value that it approaches with respect to time. It starts at 0 right here, and then goes up in increments, right? Well, not increments, I should say. It goes up in certain percentages. So we've got, after one time constant, about 63.2%. So we'll say 0.632 right there. And then we got 86.5. So let's say that that's somewhere like around here, 0.865. And then we've got 95, let's say 0.95. And then we've got 99.3, and so on and so on. 97.2, 99.3. That goes up, right? So let's just mark off some locations here. We've got at 1 tau, we're at 63.2%. 2 tau, we are at 86.5%. 3 tau, up here. 4 tau, we're even closer, really close. 5 tau, we're basically there in terms of this graph. This is what we've got going on. I'm going to attempt to connect these with a smooth line. It never happens, right? It just doesn't. But you can kind of see the flavor of it. I'm going to draw it in, then I'm going to move my points around a little bit. That was probably not that bad. There we go. So, this a little darker would be nice. Whoosh. You get the point there. That's what it looks like. It's sharp at first, and then it levels off as time goes on. And there we go. That's the behavior of the system. So what else do we have here? Well, besides the graph, nice graphical representation and the function itself, Q of t is equal to Q max times 1 minus e to the negative t over RC, we've also got some other quantities to deal with, such as the potential difference across the capacitor as a function of time. Delta V sub c of t. Potential difference across the capacitor. With respect to time, how are we going to get that? Well, we can look to the definition of capacitance being that it has to be well defined at any given time, which is then, other than 0, which is then equal to this. Boom. So how do we get delta V sub c of t? We've got that delta V sub c of t is going to be equal to Q of t divided by the capacitance itself. Just rearrange that. And what do we have then? Delta V sub c of t is going to be equal to Q max divided by c multiplied by 1 minus e to the negative t over RC. So then it comes into play, well, what is Q max divided by c? Well, Q max divided by c can be recaptured as well. When the capacitor is fully charged, it has a maximum amount of charge across its plates and will carry the potential difference across its plates that the source potential does. So what's Q max divided by C? That's equal to the source potential. So this reduces down into delta V sub C of t is then equal to this, the source potential, which is equivalent to the maximum potential difference across the plates of the capacitor, times 1 minus e to the negative t over RC. What would happen after one time constant? Well, after one time constant, we have 63.2% of the source potential difference across the plates of the capacitor. After 2, 86.5%. After 3, 95%. And so on and so on. So the point with this is that it has to mirror the changes of the charge accumulation of the plates of the capacitor. Because the ratio of the two always have to define the capacitance. All right, well, we've also got the resistor, right? We've got a potential difference across the resistor and a current through the resistor, which is equivalent to the current in the circuit at a given time. So now the resistor. Change the colors here. We have I of t and delta V sub R of t. Current as a function of time, and potential difference across the resistor as a function of time. So current and potential difference through and across, current through, potential difference across, resistor with respect to time. So how are we going to get those values? Well, let's start with the current, right? Current is the first time derivative of charge. So if we just go back to this, we've already done this. That's right, we've already done this. What does this equal? Well, we take the time derivative of Q of t, which is just Q max times 1 minus e to the negative t over RC, and we've got ourselves the current. What is that going to be equal to? Well, that ends up being Q max divided by RC times e to the negative t over RC. That's what we've got. Well, what's Q divided by RC? Let's see. Let's see what that could possibly be. What is Q max? Do we have that written up here anywhere? Yeah, we can write out what Q max is from this. Q max is the same as E times C, right? So from this, from again capacitance, Q max is the same thing as E times C, the source potential times the capacitance. So what is this then equal to? Source potential times the capacitance divided by the resistance times the capacitance times e to the negative t over RC. Well, the capacitance cancels out, and we've got E divided by R times E to the negative T over RC. So what is that? Well, what's E divided by R? We can go back to resistance and say that it has to be this. It has to be delta V sub R of T divided by I of T, true, which ultimately also has to be defined at the endpoints, or the endpoint, I should say endpoint, has to be defined in terms of the maximal value. That would be more proper there. And the potential difference across the resistor is equivalent to that of the source. We will have the maximum current through the resistor. That's it. So what does this give us then? This gives us that I of t is then equal to I max times e to the negative t over RC, or I max is equal to source potential divided by the resistance. That's it. Where? So in this case, what do we have functionality-wise here? This is exponential decay. We start at t equals 0, right when we close the switch, we have the maximum current. Why do we have the maximum current? Because there's no potential difference across the capacitor. It's only across the resistor. And that has to be the potential difference of the entire source thing. So we start off with the maximum current. Current's going fast. It's depositing or redirecting. Now, depositing, we'll just say, electrons onto the negative plate now of the capacitor. Quickly. Well, the capacitor is charging up quick at first, right? But what happens as time goes on? The capacitor becomes more heavily and heavily charged. The current dies down because the rate at which the capacitor is charging slows down. And that's, again, connected with the current. Exponential decay here. If we were to plot this out, we just have something that goes, decays down to 0 as time goes on. And so to find a time constant and stuff, similarly to what we did, we're not going to do that for this, but get the idea there. Just got exponential decay. Here we would have I max, I of t, And then we've got time. And it approaches 0 as time goes on. All right, that leaves us with one more thing to look at, and that would be the potential difference across the resistor with respect to time, which is now pretty easy to get. There's a couple different ways to get it, but nonetheless, I think right now the easiest way to get it would just be through this. We know how the current varies with respect to time. The current times the resistance is the potential difference, so we've got the delta V sub R of t is equal to R times I of t, which is then equal to R times I max times e to the negative t over RC. What's R times I max? Well, we could come back to something like this. R times I max is just the source potential. So this is equal to source potential difference times e to the negative t over RC. And there we go. There is delta V sub R of t, exponential decay, just like we have with the current, because the ratio of the potential difference to the current has to be a constant. So they have to vary in the same way, and that's what they do. So the bigger picture with this, we close the switch, boom, we have a maximum potential difference across the resistor, which drives a large current. That large current takes electrons from this plate, deposits them over here. And as more and more electrons deposit over here, the current gets smaller and smaller. Why? Well, because as more and more charge is deposited over here, the potential difference across the capacitor increases, right? Well, that means that the potential difference across the resistor has to decrease because we have to have conservation of energy. That's what the loop rule stated in the very beginning, that the sum of all the potential differences across these three elements has to be equal to 0. The potential difference supplied by the source gets split up amongst the resistor and the capacitor at any given moment in time while it's charging. And those two potential differences have to add up to be the potential difference across the source's terminals. So starts out all across the resistor. As time goes on, it splits up. When it's lower across the resistor, we have less current. And then eventually, it's all across the capacitor, at which time there's no more potential difference across the resistor, at which time there's no more current. Because the capacitor is fully charged, all the potential differences across it. So that's the correlation with all of this. It's all interwoven together, which is really cool. So the other way that we could have gotten the potential difference across the resistor is just by going to Kirchhoff's loop rule. Because we had in the beginning E minus delta V sub R minus delta V sub C has to be equal to 0. That was our loop rule, that's what we started off with. Thus, we must have that delta V sub R is equal to, we'll move that over to that side, that has to be the source potential minus delta V sub C. And this is at any given time while it's charging. So we could go ahead and say, well, delta V sub R of t is equal to E minus delta V sub C of t. Delta V sub C of t is equal to E times 1 minus E to the negative t over RC. That is what delta V sub C is, right? We've already done it. Do we still have it up there? Yeah, right there. Ooh, the last blue line. So what happens when we go ahead and get through this? Well, we've got this term distributes through, so we'll get a negative E there, and then a plus E times E to the negative t over RC. And you should be able to see fairly quickly that we get, indeed, that this is equal to E to the negative t over RC. So what's the point of doing it another way? The point is that if you ever know what the potential difference across either the capacitor or resistor are, assuming you know the source potential, then you should be able to get the other just by the direct correlation with that loop rule right there. All right, so we'll leave that at that for now. Come back, do a little problem, and yeah, sounds good. All right, get charged up.